All right, thanks for watching. Just gonna go through a few of these problems. It's just like fluency review. I want to make sure that we can walk before we run. So try your best to keep up. I'm not gonna do every single problem, but let's start off with number one. 195 plus 154, right? Just like this. 5 plus 4 is 9. 9 plus 5 is 14. Carry the 1. 1 plus 1 plus 1 is 3. And our answer is 349. So nothing too crazy, obviously. A problem like number 2, if you're going to do the vertical method, it's really important that you have the bigger number on top, right? There's another way you can do this. You could also switch it. You can like factor out a negative so that it kind of looks like this. Use the commutative property. I'm kind of skipping a couple steps. You can do it like that. As long as you remember that that negative is right there, you can do it that way as well. But if that's confusing, you can always do it that way, just that vertical method. Always reminder that when it comes to I had somebody in my first period say, oh, well, the parentheses must mean that it's multiplication. And that's not really the case here. I understand what they were trying to say. That's just not the case here. It is just regular. I am trying to trick you. But this would be subtraction. So that 126, adding a negative is the same as subtracting that negative number. And this one, we have two minuses. So subtracting a negative becomes a positive. So you could rewrite this one as 247 plus 154. Okay. So just keep that in mind, right? And what happens when you subtract a negative number? Obviously, the two negatives become positive. We can explain this like, switching directions on the number line. But this is the easiest kind of way to explain it, right? We kind of talked about looking at the number line and looking at a different direction, right? And the number 8 is the only one that was actually, in my opinion, like super hard, actually. A lot of people, when they see M and N, when they start to see letters, they get real nervous because they think some algebra is coming their way. And this isn't really algebra at all. Just suppose you have two numbers. We have M and N. M is larger than N. So you can write M has to be larger than N, right? We don't care what numbers they are as long as M is larger than N. Now, you don't need algebra to solve this, but we can actually do something pretty interesting. We can use this inequality that we just wrote, and is N minus M. We can write that, use that inequality, M is larger than N, is greater than N. And we can actually subtract, will my purple show up? I'll use blue. Let's subtract M from both sides. And what we get is M minus M. These cancel out. They become 0, right? Which will be greater than. And then we get that N minus M on the right hand side. So it turns out that N minus M, you can switch that around, is less than 0, which means it must be negative, right? So kind of a fun introduction to some kind of algebraic reasoning we might see in proofs. So our answer is negative. Since you could say, since M, which is negative, right, has larger magnitude, it's greater than N, right? It's a partial explanation, right? That's a really good start, or at least a really good frame of mind to be in m, which is negative, has the larger magnitude, right? So a good way to kind of think about that problem. Let's do some really quick multiplication. Okay. So obviously 12 times 9. Hopefully you remember your times tables. That would be the easiest way to do this problem. But you could always do the vertical method, like so. That's a 9, believe it or not. 9. There we go. You could do the vertical method. That helps. 9 times 2 is 18, and we have to carry that 1, right? So we can't just write 18, right? We have to carry that 1 up here. 9 times 1 is 9, plus the 1 that we have right here, plus that 1. 9 plus 1 is 10. We get 108. So not too bad. This is all multiplication. So for example, 15 times 11. There's a few ways to do this. It's kind of interesting. You could do the vertical method, right? 15 times 11, right? 5, 1, so 1 times 5, and 1 times 1, so 1 times 5, 1 times 1. And then we have to add this 0 in the next spot because we're not just multiplying by that 1. We're going to do the same thing, but that's not just a 1. That's a 1 in the tens place. So really we're multiplying by 10, right? So 1 times 5 is 5. 1 times 1 is 1. 5 plus 0 is 5. 1 plus 5 is 6. And there's our 1. Yeah, there's a few ways I can explain this, right? Think about this like we can break up this 11, right? We can break up this 11 as, think of that as 10 plus 1, right? And so we have this 15 times 10 plus 1, right? And we can distribute that. Let's see, let's use this blue. That seemed to work, right? We can use that 15 and distribute it to each of these, right? And now it becomes pretty easy, right? We could say, oh, well, 15 times 10 is 100. Oops, sorry, not black. Can't see that too well, huh? 15 times 10 is 150. Plus 15 plus times 1 is that 15. And wow, look at that, huh? I wonder if my highlighter will show up. Too big. Let's make that a little bit smaller. There we go. There's my 150. Oh, wow, look at that. How interesting. Wow. How neat, isn't it? Isn't math just incredible? And we still get 165. Yeah. Yeah, so many ways to get to the right answer. This one's a little bit of a doozy. I believe your answer is like 900,000. 900 and something thousand, right? So the way you would set this up, hopefully you have enough space. We have a 0 here, so really we can kind of skip it because what are we going to do? 0 times 3, 0 times 1. 0 times 0, 0 times 8. What's the point of that, right? So we'll just skip that 0. We'll add that at the bottom there because we're going to skip to the tens place, right? 2 times 3 is 6. 2 times 1 is 2. 2 times 0 is 0. And 2 times 8 is 16. And then the next one is a little bit more because we're doing this 1 right here. We're going to do the same thing, right? We're going to multiply all the numbers in 8,013 by that 1, but that's not just a 1, right? It's a 100. So we have to drop 2 zeros here and do the same thing. 1, 0, and 8. Right? 8 times 3, 8 times 1, 8 times. I'm so sorry. 1 times 3, 1 times 1, 1 times 0, 1 times 8, and then we just add. 0, 6, 5, 1, 6, and 9. And wow, look at that. 961,560. Right, so nothing too crazy. Of course, I make it look easy, but I've been doing this for a long time. Same thing with number 18, really difficult. A lot of people freak out. M and N, oh no. Are we doing algebra? No, not really. Think of, that's M times N, right? That's M times N. Okay, so I think that's where some people had some confusion, right? And so someone actually, I had a couple people actually point out, they said, well, what if N is negative also? I said, that's a really good point. So we can just add that caveat. We'll just assume that N is positive. So greater than 0, that's what that means. If N is greater than 0, then N is positive, right? So really we have let me set this up. Really, we have a negative number times a positive number, and we know that that is going to be negative, right? Explain. Ooh, there's a lot of ways that we can explain it. Remember, we discussed multiplying by a negative number. By a negative number. As a reflection about 0 on the number line. A reflection about 0. On the number line. So if I have a number line like so, here's my arrows. Let's pretend that 0 is right here. Let's say if I have 5, and if I want to multiply that by -1, if I wanted to do 5 times -1, that -1, it's not going to change the size, it's not going to change the magnitude of 5, so we're not scaling at all. All we're doing is we are flipping it about this axis of symmetry. We're throwing it across that line, and we end up right here at -5. So that'll be really useful in geometry once we get to reflections. So kind of interesting, kind of a geometric interpretation of how multiplication can be used on the number line, how it scales numbers, and how it scales numbers, and how you can reflect it about 0. I wonder if there's I'm sure there's a deeper explanation than that, but that's all I have prepared at the moment. So let's keep moving. 21's a fun one. Yeah, 22, I guess that's kind of a continuation of 18, huh? So let's talk about some factoring. Nothing too crazy. Let's talk about some factoring. Man, some of these are hard. I just made these numbers up. So normally I'm a little bit more sophisticated. Normally what I'll do is I'll actually start in reverse. So I'll come up with some numbers. I'll say, let's just multiply. Maybe I'll do 2 to the 3rd times 3 times 7. Right? So, and then that way I know, I know that how the number's kind of easily factorable, right? We don't get all these crazy primes. 21 times 2, 42, 84, right? And so I'll say, oh, okay, that's a great number to throw in, but I just kind of made these numbers up. So one of the useful things about having even numbers, at least starting with, is it's always a little bit easier. We can just simply factor out a 2, right? So we can just take this number and factor out a 2. Think about that as dividing by 2. So 2 goes into 124 62 times, right? So think about it this way. 2 times 62 is 124. And on the reverse side of that, what I did was I took 124 and I divided it by 2, right? Okay. And so I can factor this out as well. It's even once again, so 31, right? And 31 is prime, right? So how do we know when we stopped? All these are prime numbers. 2 is prime, and 31 is also prime. We can write 124 as the product of prime numbers, raised to certain powers, times 31. So the reason why I put a little 2 here is because I have 2 2's. So 2 to the second power. All right, let's do something a little bit. Oh, this one's fun. I think this one's kind of a nightmare too. Let's do 1011. Again, I showed you a trick. There's a couple tricks. Like I wouldn't really know where to start here, except I know a couple tricks. One is, okay, so 2 doesn't work. Let's try 3. And you might be sitting there and being like, oh man, how do I know if this is divisible by 3? How do I know that? And I can give you a quick trick. Remember, it's called the digital sum. So if we take 1011, right? So 1 plus 0 plus 1 plus 1. This is a little trick. If we add those numbers up, 1 plus 0 plus 1 plus 1, well, that gives us 3. Well, 3 is divisible by 3, right? Therefore, we can conclude that 1011 is also. There's a really interesting proof of that, but it's pretty advanced. You need to know something called modular arithmetic in order to get that proof. So maybe someday, if we ever touch on some number theory for fun. So fun. All right, so let's try. Let's pull out a 3. 3 goes into 10 3 times with a remainder of 1. 3 goes into 11 3 times with a remainder of 2, and 3 goes into 21 7 times. Now I'm pretty sure this is, man, I shouldn't have chosen this one. I'm pretty sure this is prime. It's not divisible by 2. It's not divisible by 3. It's not divisible by 5. I don't think 7 can do it. 9 maybe? No, because it's not divisible by 3. I think I can call it. We can Google it if we want. Should we Google it? Let's see if I can do it this way. Is 337 prime? Yes. Wow, look at that. Yes, it is true. Yeah. So 337 is prime. Lovely. How wonderful. So this one we definitely know is also divisible by 3. Okay, so try that. All right, you get 211. And see if, run down the list, see if 211 is prime. Cool, let's keep moving. So what theorem? So some of these were straight off the notes. So just in case you were absent, or maybe maybe you were new, the first couple weeks are always a little bit hectic, with people coming and going. What theorem tells us? Each number has a unique prime factorization. That's what we call the fundamental, so super important. It's fundamental theorem. So kind of like an idea that gets, tested and proven over time. Fundamental theorem of arithmetic. I believe that's what it is, right? That's what I've been saying, right? The fundamental theorem of arithmetic, right? So if two numbers, let's say it's not possible for two, here, I'll do it this way. It's not possible for two numbers. Let's say if I have prime 1 times prime 2 times prime 3, we'll call that a unique prime factorization. It's not possible for two numbers, two different numbers, to have the same prime factorization. If they do, That is true if and only if m has to necessarily be equal to n. They have to be the same number. If they have the same prime factorization, that is a terrible double-sided arrow. If they have the same prime factorization, they necessarily must be the same number. Okay. What is a prime number? List 10. Don't worry, I'm not going to list 10, but I can tell you a prime number is any number with exactly two prime factors, namely 1 and itself. 1 and itself, right? So in fact, this definition is kind of interesting because you learn that 1 is, that's a long I, 1 is not prime. Kind of fun, kind of interesting result. Number 34 is really hard. I'll help you out with one thing. You need to be able to factor this negative 24. So you need to be able to say 1 and 24. You need to know that 2 and 12. You need to know that 3 and 8. You need to know that 4 and 6. And so you need to be able to factor a number in order to do this polynomial factorization. And the reason being, why do you need to know all of them, is because you need to know which pair of these actually can you combine to create negative 10. So it turns out that this is the prime factorization, and we actually need to make that, I'm so silly, sorry, it's not 3 and 8, duh, it's 2 and 12. Sorry, it's late. We need to make that 12 negative, right? So the way we would actually do this is, people always skip this step, which I kind of find a little bit perplexing in algebra class. When we're trying to factor this, what ends up happening is you rewrite that negative 10x as these two factors. So it's kind of an interesting little puzzle. You factor out that x, you get x minus 12. You factor out this 2, and you get x minus 12. And how cool is that? It's like a puzzle. Very interesting and cool, right? I already answered number 35, so don't worry. I'm not asking you guys. We haven't covered this at all. Some of you guys are not even taking algebra right now, so we don't have to cover that, so don't worry. And last one, greatest common factor. You know, again, forgive me if this seems a little juvenile. It's just, these are things I want to kind of cover a little bit. Just say, hey, you remember at the beginning of the year, if we ever run into like any type of fluency issue in terms of like math, you know, sort of arithmetic or like simplifying fractions or whatever, I want to be able to say, oh, do you remember when we did this? Now the GCF is kind of interesting. We have there actually is I don't know if I'd call it a shortcut, but if you want to Google it, it's called Euclid's algorithm. Kind of an interesting way to find. This is not what we're going to be doing. We're not going to be using Euclid's algorithm, but it is something interesting that you can use if it makes sense to you. I will definitely not be mad at all if I see somebody study and do Euclid's algorithm. So we're going to do it kind of the old school way. We're going to actually list out all the factors of each of these numbers, and we'll just find the greatest of those two, right? So let's make like a little T-chart kind of. We'll put our two numbers that we need to factor. So 1 is always going to be a factor. It'll always be your first one. These numbers are both even, so 2. 3 does not go into 20, but 4 does. 5 does, 10 does, and then of course 20 itself does. Let's factor 28. 1 goes into it, 2 goes into it, obviously, like we said. 4 goes into it, 7 goes into it, and I think that's 14 goes into it, and then 28. And then obviously the greatest of the two the greatest factor that they have in common, the biggest number that they both have in common is 4. Therefore, that's our answer, right? So these things can just be kind of tedious, honestly. It's just kind of a pain to deal with sometimes. So a little trick, if you're really, this helps if you're really good with like your math facts, you know, your times tables or whatever. You'll notice that it kind of like flips, right? You notice I have 3 and 3, and same thing here. 3 and 3. So you can think of it as 1 and 28, 2 and 14, and 4 and 7, right? 1 times 20 is 20, 2 times 10 is 20, and then 4 times 5. So I kind of know when I'm done. When I hit 4, right, I was like, well, 4 times 5, and then now I can start going backwards, 2 and 10, and 1 and 20, right? So there's a little bit of a symmetry there in terms of the factors. It's kind of a little bit helpful. Let's do maybe one more. I'll do 50. Oh, should I do 54? Oh man, I feel like I'm gonna regret this. We'll do 50. I want to do 54, and I want to do this one because of that symmetry thing I was just explaining. There's a little something neat about 81, how it's a perfect square. So there's something I want to show you. So 54 and 81, obviously 1 goes into both of those. 54 is even, but 81 is not, so no 2 here. 3 goes into 54. Does 4 go into 54? I don't believe it does. It must. 4 does go into 54. 17 times. 5. Does 6 go? If 6 goes into 54, 9 times. So there's my line of symmetry, right? There's my line of symmetry. I know that 6 goes into 54 9 times. So 6 times 9, and now I can start working my way backwards. 4 goes into 54 17 times. 3 goes into 54 8. What is that? It is that true? 4 goes into 54 14. Wait, does 4 not go into 54? It must go into 54. Give me 1 second. Let me double check. It doesn't? Oh, maybe I'm wrong. 4 goes into 54. 1. Carry the 1. 14. 4 doesn't go into 14 evenly. Huh. I guess not. Sorry, my mistake. We're going to pretend that didn't happen. 54. I told you I was going to regret this one. 3 goes into 54 18 times. So, yeah. Forget about that. Sorry about that. I was so convinced. I see why. I know why. I fooled myself. 2 goes into 54 27 times, and 1 goes into 54 54 times. 81, 1 goes into it, 3 goes into it, and 9 goes into it, and 81 goes into it. 3 goes into it. Sorry. Believe it or not, I'm actually not super good at calculation, as you can probably tell. 3 goes into it. I should have known that without even having to divide. And so our line of symmetry is actually around that 9 because it's 9 times 9. So just kind of an interesting result. That's how I kind of figured that one out. But we can get rid of these lines because they're kind of irrelevant to us now. And so we can see what's our greatest common factor. It looks like 27. 27 is our greatest common factor. I wouldn't have guessed that. Neat. So I guess 54 and no. Cool. All right, that's that. I'm gonna call it a day. So just yell if you have any questions. Let me know. And much appreciated. Thanks for watching, guys.